My name is Chuck Acton. I'm the English manager at JPL, and we're very happy to be here to help get you going on your SPICE adventure. Please raise your hand and speak up if we're speaking too quietly or too fast or in the wrong language, and we'll try and fix it. Nat can do it in French if necessary, and Boris can do it in Russian. I'm stuck with English, unfortunately. So the purpose of this class is to give you really an overview of SPICE. It's really just an introduction, how SPICE is used, what are the various pieces of the whole SPICE system, some examples of using SPICE software, conventions, which is a very important part of SPICE because there's lots and lots of conventions, some of which are obvious and some of which are a little confusing. We're going to have some programming exercises, and in most classes the students say that's the best part of the class, so we hope you'll really look forward to that. That's where you really get to get your fingers used to writing SDK calls and things like that. We'll talk a little bit about common problems that are encountered by people using SPICE. Sure enough, there are quite a few of them. We're going to hope you can be aware of them and thus avoid them yourselves. And we're going to describe the various resources that we and ESA offer in support of your using SPICE. We also hope to get a little bit of feedback at the end of the class, both about the class and about the SPICE system. And of course, if you're brand new to SPICE, you're probably not going to be able to give us too much feedback, but we're interested in any sort of feedback you're able to give us. And I think Mark's got a form he'll pass out at the end. As I said, these tutorials will only help you to begin using SPICE. You will not walk out of here being experts. It's going to take some time, both studying our material after the class is over and actually trying to use SPICE and running into problems and answering questions yourselves. The more you use it, just like learning to ride a bicycle, the more you try it, eventually it becomes natural, but it's going to take a little bit of time. The tutorials that we're presenting today are in some cases smaller ones than the ones that are available online. The online ones have, in some cases, more information, and we hope that after this class is done, you'll download and refer to the online tutorials rather than the class tutorials, because there's some important details there that we just don't have time to go through during the class. There's a few topics that are really not addressed much at all, and that is producing SPK files, producing CK files, really producing most kernels. We don't talk about archiving. That's this guy's job over here mostly. And again, we have these open book programming lessons. That's the fun part, and we'll spend quite a bit of time working on them. We'll be here to help you. These truly are open book lessons in that we present a problem statement, we tell you about the data that are available, we give you a few tips about how to address each little task, and then we give you a drawing, in some cases, showing you graphically what we're asking you to do. And then we say, go and do it. We give you 40, 50, 60 minutes to do each lesson. The actual code that we wrote, the answer, if you will, is sort of on the next page. And if you want to cheat, you can just flip ahead in the lesson a little bit, and there's our answer. And also the numeric answers for most of the exercises where there are numeric computations. But instead of doing that right away, we hope that you'll struggle a little bit and think about the tutorials that we have just presented and the other documentation that Boris will describe, and try and answer the question by looking back at that material, because that's what you're going to have to do later on when you're on your own, unless you have a nice colleague next door that knows all about SPICE. So part of this class is just to get you used to the process of figuring out what it is you're trying to do and what materials are available to help you find the right subroutines, find the right descriptions and the common problems that will help you get through any issues that you've had. In the class, if you're struggling a bunch, we don't want you to spend the whole time struggling and never get through the lesson. So please raise your hand, and one of these three smart gentlemen will stop by and hopefully not give you the answer to your question, but give you a hint about how to go about answering the question yourself. Again, we're trying to train you in the process of using all of these materials. If that isn't really working, don't struggle. Just look ahead at our code and see what we did, at least as far as to the extent, or the point in the program where you are, and use that so that you can keep going, because it's really good to try and go all the way through all of the exercises. By the way, the exercises sort of build on each other, so we want you to, if you miss the first one, you're going to maybe struggle more with the second one and more with the third one. So we'd really like you to try and go through each one of them. I think we give plenty of time for the lessons, but it's always tough to know how much time to give. Some people are already familiar with SPICE and they just zip through it like that. Some people never heard of a quaternion before or something like that, and it's a real struggle. We tried to pick a balance, and if you get done with the lessons ahead of time, we're going to give you some suggestions about sort of extra credit work. You don't get extra credit, but you can learn a little more by doing it. And eventually, when the time is up, we'll have to say, okay, time's up, time to go on to the next lecture or set of lectures, and then get another lesson, programming lesson. And I think it's always nice to know, who you're working with. So there's some happy people here and some not so happy people here. I brought the happy ones with me. So Boris is in the back. Raise your hand, Boris. And Matt, wave your hand. There were 3 of the 6-member Dave team back at JPL. And of course, the happiest person of all, and the guy that knows most about it, is your sponsor of this class, Mark. And so he's your, as he said earlier, he's your go-to guy, not just for this class, but for all things about SPICE. He's the European SPICE expert, and we just heard this morning that later on this year, he's going to have a new person added to his growing domain to help him support all of you folks. So that's the introduction, and I brought my glasses with me. I can find the next one. Okay, so this is kind of a grand overview of SPICE, and as I said earlier, those of you who've already been using SPICE will find this
eventually it comes up, but I'll have to look this.
all right, there it goes. Those who already know about SPICE will find probably this is a little bit boring, but stick with it. So what can you do with SPICE? Let's get right into it. Well, you can compute a variety of observation geometry parameters. Here's an example: the position and velocity of any one thing relative to any other thing. So planets, satellites, comets, asteroids, are just some of them. You can compute size, shape, and orientation, or you can retrieve size, shape, and orientation of these same natural bodies. You can get the orientation of the spacecraft, which is clearly important because you want to know where your instrument is pointing. And, in fact, project your instrument field of view into space, whether it's on the surface of a planet or off at the star field. This is the standard and the old-fashioned kind of SPICE stuff. Compute some quantity at time t. Well, a few years ago, maybe more than a few years ago, we realized people were interested in sort of the opposite question, and that is find times when a specified geometric condition is true, or when a specified geometric parameter was within a given range or had a given value. Examples, so when is an object in occultation, or in transit, or when is a spacecraft within some altitude range above the surface, or when was an instrument actually pointing at a particular object of interest to you. So these kinds of questions return a set of time intervals when this condition is true. You specify a constrained window, and you say within that window find all the times when my question is true or when my parameter was within a given range or had a particular value. So some examples of how SPICE is used. Well, before a mission is launched, you might want to evaluate it. How will the planned trajectory yield, or will it yield the kinds of observations I want? Will we come close enough to the body of interest, or will we see that body with the right lighting angles, or will we see it at the right latitudes and longitudes? So very much SPICE is used in the planning process. For engineering purposes, there's a variety of uses, and this is one where you're asking, can my deep space station see the spacecraft at certain times? Planning an instrument pointing profile, at least for those missions where you can either move the spacecraft or point an instrument, and you want to plan how to orient your instrument to achieve the science observations of interest. Often a picture is worth 1,000 words and an animation is worth 10 million words. So we've added very recently an animation capability to SPICE so you can visually see representation of all this geometry. And I don't know, if you're like me, I wasn't much of a believer in this sort of thing about 20 years ago. Well, I'm a total believer in it now, and I see Boris, Mark, and a bunch of other people make use of this visualization tool all the time, and it's really, really quite helpful. It goes way beyond just sort of education and public outreach. It can be very, very useful for understanding what was going on during the mission, understanding if SPICE data makes sense or not, things like that. And of course, the original purpose was for science data analysis and producing the archive necessary of your science data so that it can be used for 10, 20, 30 years in the future. If I try to summarize SPICE in one big graphic, here it is. So at the core of SPICE are a bunch of data files, what we call ancillary data files. We call these kernels. So kernel equals data file equals kernel in SPICE. Don't let that word kernel confuse you. Okay, some of those kernels are produced using some SPICE utility programs, and you'll hear mention of those during this class, but we won't go into actually using them in the lessons. And some of them are produced just using the text editor. So there's two ways, and I've shown down here which kinds of kernels are produced in each of those two processes. Okay, once you have those kernels, well, you got to do something with them, because you want to compute latitude, longitude, lighting angles, whatever. So you have to write a program, and that's what we're going to be teaching you about today mostly. You're going to write this red program, and it'll have mostly, not in this class, but in the future, your own modules, your own subroutines, and a few SPICE toolkit subroutines. That's the part you'll be studying mostly today. And when you do it correctly, out will come the derived quantities, what we call observation geometry, latitude, longitude, lighting angles, altitudes, so forth and so on. And of course, what I don't show on this graphic is, well, we'll talk about that in a second. So let's look a little more at ancillary data. What are ancillary data in the SPICE context? Well, we start with a flat solar system. Some people know the Earth is flat. The solar system is also flat, shown here in pink. And in that solar system, we have a whole bunch of objects We have natural bodies, sun, earth, planets, satellites, comets, asteroids, and spacecraft, unnatural body. We have reference frames for all of those. Now, a lot of times people call these coordinate systems. In SPICE, we're very careful to distinguish between reference frame and a coordinate system. We'll talk more about that later on, so I don't waste time on it now. Now that we have reference frames, we can define position and velocities in those reference frames, position and velocity of any one thing relative to any other thing that's known to SPICE. We can also compute orientations, and that involves both the orientation of natural bodies and of spacecraft. And for natural bodies, we can also obtain the size and shape of those bodies. Underlying all of this is time systems. Time is the independent variable that connects all of the SPICE data together. And in planetary science, at least, and in some of the other kinds of space science, there are multiple time systems used, and you have to be able to understand them and convert time tags between these systems. You'll be hearing more about that during the class. All right, so that's the ancillary data, but I added one more thing here, and this is really not ancillary data in our terms. This is really a derived quantity pointing, but it's such an important portion of SPICE that I wanted to add it on this figure anyway. How do you use these data? Well, you can, again, find out where the spacecraft was located, how fast it's going, how it's oriented, how the instruments are oriented, location, size, shape of the target bodies, and where an instrument was looking on the surface, let's say. In the words there, I'm talking about past tense, but you can do it for future tense too, and that's how you go about using SPICE for planning observations. Where do these data come from? Well, some come from the spacecraft. In particular, spacecraft orientation usually comes from an inertial measurement setup on the spacecraft. Some come from the Mission Control Center, particularly the spacecraft orbit comes from flight dynamics people at ESAC for most of your missions. Some come from spacecraft and instrument builders. That is, where are all the pieces on the spacecraft and how are the instruments mounted and aligned on the spacecraft? What are the instrument field of view, size, shape, and orientation? Some come from science organizations, particularly the IAU, and that's where we get the size and shape data for all the planets and satellites. And the orientation as well, the spin conditions. And SPICE simply organizes data from all of these sources into a convenient set of packages, what we call the SPICE kernels. And no matter which mission or where the data are coming from, SPICE so far has been able to always find a way to ingest data from all these missions, all these sources, into this fixed set of kernels. And that way you have a fixed kind of data to work with to go and do make derived computations, observation geometry. So why use SPICE? Well, clearly knowing this geometry is important for a lot of investigations. And there's very few instruments, I think, that do not need some knowledge of SPICE. Some of them, high-resolution camera needs an awful lot of geometry information. A fields and particles instrument needs rather less geometry, but it still needs to know some kind of geometric information. So there's other ways of making those computations. Probably some of you are using other methods. Why use the SPICE system? Well, that's a good political, philosophical question. Our belief is that if you learn SPICE, you'll be able to use it over and over and over again. And that's because the NASA missions, the ESA missions, JAXA missions, Indian missions, Russian missions are all using SPICE, at least the planetary missions are. So it's been adopted so widely that to a certain extent you can count on being able to have SPICE data from each new mission. Just before we started this class, we were talking with some of your managers about using SPICE on JUICE, which is going to use SPICE, Bepi Colombo Solar Orbiter. You have to invest time in learning SPICE, no question about it. You're going to learn that in spades this week, but having made that investment, we believe you'll be able to use it over and over again. A little more look at SPICE components. We've talked about these ancillary data files, and we've talked a bit about the SPICE software, the SPICE toolkit as we call it. There's also documentation, tons of documentation. You started seeing a little bit of it already. You're going to learn a lot more about it, and in the end you're going to say, Chuck, there's just too much documentation. A lot of people tell us that. I can't find my answer because there's just so much documentation. Well, we're going to try and help you understand what documentation there exists and which pieces to look at for a particular challenge you have so that you don't feel totally overwhelmed with it. We feel it's best to really provide all this documentation so that people who really want to spend some time looking at it can really find answers to almost anything, any question that you have. There's tutorials, that's what we're starting to go through right now, and the programming lessons, which we'll be doing, and the training classes, that's what we're here for, and then user consultation. That's Mr. Costa over here. He's the principal source for support for ESA missions, ESA people, but to the extent that we can, I and the other NAVE team also provide user support. Here's where the SPICE acronym comes from. It's not really an acronym, but it's a bunch of letters. And this is how it sort of translates into the real data files, the kernels that you'll be using. And in the next charts, we actually expand on that a little bit. So SDK files contain position and velocity of something relative to something else. Typically a spacecraft and planets and satellites, but it can also be some very strange sorts of things, things you wouldn't think would be described by an SDK file. We'll get into that later. Planetary constants has size, shape, and orientation of natural bodies. It could also have some similar information, geometric information attached to or associated with the natural body. Instrument kernel contains the instrument field of view, size, shape, and orientation. Again, it could have some additional instrument information as well. C kernels are providing principally the spacecraft orientation, but sometimes there's a scanning instrument or scanning gear within an instrument. You can make a C kernel for any of those articulating structures as well. The events kernel is something that we came up with at the early days, but it really hasn't been very successful, so it's not much used, at least in NASA missions, and who knows what will happen in the future. So we're not going to really talk about the events kernel at all. There's some additional kernels that don't fit into the SPICE acronym, all very important. The frames system came along sometime after SPICE had been invented. And that ties a great deal of the SPICE data together. It tells you how to transform information in one reference frame to another. And in planetary missions and heliophysics missions, there's typically many different reference frames used, sometimes dozens of them. Leap seconds kernel is used to provide data needed to transform between UTC time and ephemeris time, where ephemeris time is the underlying fundamental time system used throughout SPICE. S-clock is also a set of calibration information used to transform between spacecraft clock time tags and ephemeris time. So these two sets of correlation information allow you to transform between most time systems used in the space science domain. We have a new item, fairly new, called the digital shape kernel, and this is a way of providing high fidelity information about the shape of both small irregular bodies like comets and asteroids, and also large regular bodies like the Earth or Moon that have some topography that you want to have carefully modeled. So in a sense, the DSK is a new version of a planetary constants kernel, where PCK just provides triaxial ellipsoids as shape data. DSK goes into much more high precision, high fidelity modeling information. Okay, the SPICE toolkit. The contents, the biggest thing is a large collection of subroutines. There's a huge number of them, but don't worry. Typical users such as yourselves only use a handful, 5, 10 routines to do almost anything. There are some programs, utility programs. Some are used to help produce SPICE data, and some are used by you to help manage SPICE data, to summarize the contents of the kernel, for instance. Tons of documentation. You'll hear more about that later. And as you're all now aware, the toolkit exists in 5 languages. By the way, the Python one that most of you are using was actually written by a student, really, who did a really good job. We haven't actually made a Python toolkit ourselves. We support most of the popular platforms, and where it's appropriate, several compilers. So at the moment, I think we're supporting 44 different instances of the SPICE toolkit, all built ahead of time, all tested ahead of time, so all you have to do is download the correct version and for your platform and for the language of interest, and you're ready to go. Okay, how do you use all of this stuff? Well, here's that user's planning program, in this case, the big red box. And it consists mostly of subroutine modules that you've written, but also a few selected SPICE toolkit modules. And then that program ingests any number of SPICE kernel data sets that are needed for whatever job you have. You would never have to use all of them. I showed all of them here, but you would never use all of them in a single program. Maybe there's some other data that goes in as well, and out comes your answers. Again, this is a planning program, so it might be somehow an evaluation of a planned orbit, or of an instrument pointing plan, or maybe data needed to do visualization, or analysis of telecom performance if you're doing engineering functions. All right, well, let's look at another example. Here's science data analysis, and just for fun, I broke this up into 2 steps. And so you, the scientist, again, wrote your own program using some of your own modules, some SPICE modules, and you computed a bunch of geometry, let's say latitude, longitude, lighting angles at every time a picture was shuttered. And you put those into an intermediate file, this derived observation geometry file. And then you have a second program that reads that nice tabulation of geometry, as well as your science instrument data and calibration data, and out comes your award-winning science paper results. Here's a third way for using SPICE, and you'll hear more about that later on if you haven't already heard about it. In this case, you don't have to write a program at all. You use our web geocalc tool, which is a client-server kind of a tool. And you have your own computer in which you bring up this tool in a browser, and you tell it what you want to do and which data you want to work with. You punch and fill in the various parameters that are needed by the computation to come up with the answer you have. And our geometry engine will compute your answer and send it right back to your browser. And there you get on your screen some numeric results and optionally some graphic results. So it's a way of doing rather quick computations. Let's say you're doing a peer review of somebody's paper, or you're trying to validate your own pipeline process where you've written a SPICE program using subroutines, but you wonder, did I do that correctly? Well, maybe you could use web geocalc to check as a sort of a gold bar check of the program that you wrote. Or maybe you're in a meeting and someone says, hey, does anyone know what the altitude is going to be at such a time? And right there, boom, you can answer the question right during the meeting. Some characteristics of Spice, the software is portable between computers. You've seen that. We have 4 different computers supported. New toolkits come out on an irregular schedule. It's only when we think we have enough new capability that we release a new toolkit. It's not every month or 6 months or something like that. The code is very well tested before we pass it out, whether it's right or not. Our feeling is we only get one chance with you guys. And if we show you buggy code, you're going to say, I don't want to have anything to do with that Spice stuff, and that's the end of it. Now, you may not really have that choice. If your project has said we're going to use Spice and there's nothing else, well, maybe you're stuck with it. In any case, we try very, very hard to test the code very thoroughly before we pass it out. So it's rather rare that a Spice user outside of our own 18 finds a bug in the software. It does happen once in a while, and we find occasional bug, but it's pretty rare. Toolkits are always backwards compatible. So if you wrote a program using a toolkit from 6 years ago, and you want to you change your program today, and you want to relink to today's toolkit, we guarantee that our software will work the same as it did 6 years ago. I think we're very, very close to being very truthful in saying that. So we spend a great deal of time to maintain backwards compatibility, unlike Microsoft software or some other kinds of software. We provide you the source code, and it's very highly documented. Some people say too highly documented. The code includes built-in exception handling, so we try very hard to capture your inputs and analyze them, and if it's a mistaken input, we'll give you an error message. Spice error, blah, 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 blah. Describe where it occurred and why it occurred, at least to the extent that our software is able to determine that. So when you start doing the programming lessons, you'll undoubtedly see some of these Spice error messages, and they're intended really to help you figure out what you did wrong and fix it. Some more characteristics. Everything is double precision, all the computations, so it's very high accuracy. There are a few times when maybe quadratic accuracy would be useful for radio science, but for the most part, double precision works for science investigations. You can port kernels between different kinds of computers, PC on the one hand and Mac on the other hand, for instance. Kernel files are separable. I showed you some diagrams where all of the kernels were being fed into the program you wrote, but I told you that's an unrealistic case. You only use the 1 or 2 or 3 kernels, perhaps, that are needed for whatever job you're doing. And maybe the best part, all of this stuff is free from the nasty US ITAR and licensing restrictions and everything like that. And also, all of this stuff is free to you. You're free to use it. You don't have to pay us anything. You don't have to sign up with us. You can just download it and use it to your heart's content. We've been through this, the portability and the fact that we have ready-built packages for all of the different platforms and environments. You could use Spice on almost any kind of a space science mission. We even say balloons and aircraft, and we haven't actually had that kind of a mission yet, but there's no reason why it couldn't work there. It's used beyond planetary science, and now we have heliophysics using some Earth science missions. Some observatories, at least in the U.S., use it to have their telescopes point at various satellites and so forth and so on. There's even in the U.S. military use of it. It was initiated way back in 1984, a precursor to Spice. The current system, though, started really around 1991 with the Magellan mission. So it's been in use for a long time, and that's one of the reasons we can say that, it's pretty solid code because we've been through all of the bugs early on, and there are not many, we think, left, at least in the older code. Original purpose for SPICE, again, was for science analysis and archiving, but it was quickly learned that you could use it throughout the whole mission life cycle, and that's what we see today. It's widely used from pre-phase A through 10 years, 20 years after the end of the mission. SPICE is not a requirement in any of these environments. You don't have to use it if you're working with NASA missions, but most NASA missions have chosen to use it. International Planetary Data Alliance, which is slowly growing up, has SPICE as a recommendation, but again, not a requirement. Within ESA, it's Mark can decide whether it's a requirement or a sort of option. Again, you may not have too many other options. And SPICE data is available for at least some of these other agencies in their archives. And this is sort of a final chart, just as eye chart, but it's just again to give you an idea that it really is pretty widely used, has been, and is currently, and is planned to be widely used. So we're using this chart to try and convince you that, yeah, learning SPICE is worth the investment in time, because you should be able to use it well into the future. So we offer this set of building blocks for you to write your own programs to do planning and analysis and engineering functions on various spacecraft. So I probably went way over my time. Any questions at this point? We'll cover almost every topic will be covered ad nauseum over the next couple of days. All right?
We're actually ahead of time, so.
Oh.
What kind of support do you provide outside of these workshops for the community? I know that there was a mailing list.
So the question is, what kind of support is provided to people like you after this class is over? We'll talk about in one tutorial the various resources available from the NAIF server. Mark will talk a little bit about resources available on the ESA side. And as I said earlier, we have consulting from Mark and to a limited extent from NAIF guys as well. You know, it's always a question for us guys how far we're supposed to go in supporting ESA people. In a few cases, we actually have money from NASA to support an ESA mission. Mars Express, Venus Express was going. ExoMars, TGO, we have funding to support that mission. And in the meeting this morning, there was talk about looking into providing NAIF support for JUICE and Bepi Colombo in the future. And that is yet to be worked out. But Mark's a real smart guy. He knows probably as much, if not more, than us. So and you can ask him how far he can go in terms of providing support. But again, we've tried to provide so many materials, training lessons, tutorials, technical reference documents that with this kind of an introduction at this class that you'll be able to largely support yourself in the future, perhaps with some help from a colleague next door if that person has learned SPICE, such as you, Mr. Meno.